Infrared rays were discovered by William Herschel in 1800. This came about when he was passing sunlight through a prism. He noticed that a thermometer held just beyond the red end of the visible spectrum indicated a rise in temperature. He thus concluded that this indicated the presence of some form of invisible energy. It wasn't until 1840 that his son, John Herschel, produced the first thermogram on infrared film. It has long been used as an indicator of machine condition. Nowadays, infrared temperature sensing provides a commonly used predictive maintenance or PDM technique. It allows the study and measurement of the radiant heat pattern emitted by a body. Regions of increased or decreased heat emission are often indicative of a fault. An infrared ray is an electromagnetic wave. It can be thought of as a form of light. Infrared rays are sometimes called heat rays and differ from other radiation, such as X-rays or gamma rays, in that it poses no hazard to the human body or to the measured object. Infrared is a form of electromagnetic radiation. It has a wavelength longer than visible light and shorter than radio or TV waves. Its position in the electromagnetic spectrum is depicted on the screen. Commonly called thermal imaging, although the term really encompasses other methods for tracking temperature changes in plant equipment, as will be seen later in this text. In thermal imaging, the radiant heat pattern emitted by a body is displayed in the form of a temperature map. Radiant energy differences are indicated by variations in gray level or by use of colors. This thermal map is sometimes called a thermogram. It's produced by means of a detector that's sensitive to energy in the infrared portion of the electromagnetic spectrum. Typically, optics are used to focus the image onto the detector. The resulting signal is then amplified and sent to a video processor, from where it's displayed and may be captured in a manner similar to a digital photograph. All matter comprises atoms which link together to form molecules. These vibrate against each other and thus have a kinetic energy. This kinetic energy is part of the internal energy of the object. The kinetic energy of rapidly moving molecules is referred to as thermal energy. As more thermal energy is transferred to these molecules, the vibration increases. Temperature is a measure of the average kinetic energy of the vibrating molecules of the object. As the kinetic energy of the molecules changes, the matter may undergo changes of state. Matter may exist in solid state, as a liquid or as a gas. In any given subject, the liquid state occurs at a higher level of temperature than the solid state. Similarly, the gaseous state occurs at a higher temperature level than the liquid state. Heat and temperature are not synonymous, although in general conversation the terms are often confused. When two bodies of differing temperatures meet, the thermal energy will transfer from the hot body to the cooler one until a state of equilibrium is restored. The process in which the thermal energy is transferred is called heat. In the Netherlands, Daniel Fahrenheit invented the alcohol thermometer in 1709 and the mercury thermometer in 1714. Some countries still use the scale of temperature measurement that he defined and which bears his name. The Fahrenheit scale uses the freezing point of a salt water solution as its 0 and the temperature of the human body as its 100 point. There was some refinement of this scale in later years, and it now defines 32 degrees as the freezing point of water, and the boiling point of water is 212 degrees. In countries, the Fahrenheit scale of temperature measurement has been replaced by a system devised by the Swedish astronomer Anders Celsius. The Celsius scale uses the freezing point of pure water as its 0 and the boiling point of pure water as its 100 point. We saw in the last slide that the Fahrenheit and Celsius scales do not compare directly in terms of temperature difference because they use arbitrary and different 0 points. When using thermography as a practical tool, we're often concerned with temperature change or difference. So, when considering and evaluating temperature change, it's important to take into account the actual measurement scale that's being used. Temperature change is commonly referred to in thermography as delta T. In the lesson Background Science, we learned that heat is thermal energy in transit and that it flows from a point of high temperature to a point of lower temperature. The laws of physics tell us that energy cannot be created nor destroyed, and so all heat must be accounted for. There are 4 mechanisms by means of which thermal energy may transfer from one body to another. These are conduction, convection, change of state, and radiation. In a given situation, any or all of these mechanisms may be evident. The simple example depicted on this scene illustrates all 4. Conduction is the only method by means of which heat can flow through a solid body. Faster vibrating molecules in the hot part of the body collide with slower vibrating particles in the cooler part of the body, and in doing so, kinetic energy is transferred. In consequence, the faster molecules slow down and the cooler molecules vibrate faster until a condition of thermal equilibrium is reached. The molecules do not leave their mean positions. If a temperature gradient exists, then convection may occur through movement of a fluid, that is, a liquid or a gas, or between a fluid and a solid. In convection, thermal energy is transferred in part through molecular collisions, similar to conduction, as well as through displacement of the molecules from their mean position. This displacement occurs naturally as the warm part of the fluid expands and rises to be replaced by the denser, cold part of the fluid body. In some cases, this effect may be accelerated by use, for example, of a fan, in which case this is called forced convection. When a substance is being heated through a change of state, that is, solid to liquid or liquid to gas, the temperature doesn't change. Instead, it stays constant until the change of state is complete. Thus, all the heat that's given to the substance during the change is known as latent heat or hidden heat. The same effect occurs as a substance cools through a change of state. As ice melts, it changes from ice at 0 degrees Celsius to water at 0 degrees Celsius. Similarly, water boiling at 100 degrees Celsius changes to steam at 100 degrees Celsius. This shows that some of the thermal energy is used in achieving the change of state. This apparently lost thermal energy is called latent heat. Within plant maintenance, the term thermography is most commonly used to describe the use of thermal images for subjective or qualitative identification of hotspots that may be indicative of problematic conditions. If the image is corrected to take factors such as surface variances, atmospheric conditions and instrument characteristics into account, then a more accurate quantitative analysis may be undertaken. The term quantitative thermography encompasses the use of infrared devices that can be used to obtain spot temperatures from a target, such as the infrared probe shown here. Radiation results from electromagnetic energy generated by the movement of charged atomic particles. We're most familiar with the phenomenon in the form of light. Thermal radiation is similar but occurs at a different wavelength, invisible to the human eye. Radiation is characterized in terms of wavelength and frequency and travels at the speed of light. The infrared portion of the electromagnetic spectrum is broad. It's divided into regions as indicated on the screen. The different regions represent different temperature ranges. Typically, longer wave infrared detection is more sensitive to lower temperature emissions. Most normal thermography is undertaken in the longer wave infrared regions. When radiation falls upon a body, some will be absorbed, some will be reflected, and some will be transmitted through the body. The percentage of energy that's absorbed is termed absorptivity and is written lambda A. The percentage of energy that's reflected is termed reflectivity and written lambda R. And the percentage of energy that's transmitted is termed transmissivity and is written lambda T. All energy must be accounted for, and so lambda A plus lambda R plus lambda T must equal 100% or 1. For industrial thermography purposes, we can say that most target objects will be opaque to infrared, that is, lambda T will be 0. We can therefore say that lambda A plus lambda R equals 1. Emissivity refers to the amount of radiation emitted by an object. Kirchhoff's law tells us that the amount of radiation absorbed by an object will equal the amount of radiation emitted. This holds good for a specified wavelength, temperature and direction. In a practical sense, this tells us that highly reflective objects are poor emitters of infrared radiation, whilst objects that absorb well are good emitters. This means that when making quantitative comparison of temperature differences using infrared measurements, you have to allow for any differences in the emissivity of the target materials. The emissivity of a material is often expressed in comparison to the emissivity of a so-called black body. This is a theoretical object which is a perfect absorber and which therefore has an emissivity of 1. It does not exist in the real world. The emissivity of real bodies varies between greater than 0 and less than 1, according to wavelength. A perfect mirror would have an emissivity of 0. For many inspections, the variations in atmospheric conditions will have negligible effects. However, steam, water or vapor in the air can have an impact on measurement accuracy. Water will absorb thermal radiation and will also add its own emissions to what the thermal camera detects. In cases where it's impossible to take measurements without the presence of water, it may therefore be necessary to make appropriate mathematical corrections to the data. Thermography is but one tool in the predictive maintenance toolbox. The benefits of condition monitoring in general are well documented. Specific advantages applicable to thermography include those listed on the screen. The price of thermal imaging cameras has dropped considerably in recent years. However, for many small companies, the equipment cost may still be an issue. Therefore, a number of organizations offer equipment for hire on an as and when required basis. The technique requires dedicated and trained personnel to achieve optimum effect. For this reason, it's common to outsource the activity. Modern infrared cameras are compact, reasonably rugged, and readily portable for site use. A wide range of equipment is available, offering varying levels of sophistication to suit individual applications and budgets. Basic controls on the camera will typically include focus, range, span, and level. Focus control on a thermal imaging camera works just like it does on a regular camera. It controls the distinctness or clarity of the image. Thermal imaging is a visual technique. It relies to a large extent on visual recognition of suspect plant parts or components, and it's therefore important that the image is clear enough to allow this. The range control relates to the ranges of measurements that are to be studied in the target objects. The camera must be set to accommodate all of the temperatures on the object that may be of interest. Infrared camera, the level and span controls correspond to the brightness and contrast controls on a TV set and provide further aids for image clarity for the thermographer. In the lesson Radiation Basics, we learned that highly reflective images require some care in interpretation. We also learnt about the need to take emissivity into account when looking at thermograms. When considering temperature differences exhibited by thermograms, there are other factors that must also be accounted for, such as emissivity of target materials, reflections, geometric differences, and transmittance effects. The shape of a target object can affect the apparent temperature. For example, viewing an open box from its open side will expose the camera to radiation that's being emitted from a number of sides together, and may therefore suggest a higher temperature than that of the actual box material itself. In the lesson about radiation basics, the assumption was made that for industrial thermography purposes, most materials can be regarded as being opaque to infrared. In reality, some materials will transmit infrared radiation, and this can have an effect when target objects are hidden behind such materials. Examples include glass, some plastic materials, and certain types of surface coatings. Main industrial applications for thermography fall under four main areas: mechanical, electrical, energy conservation, and plant safety. Electrical equipment is probably the main application. The use of thermography for condition assessment of electrical systems probably predates the wider use of terms such as condition-based or predictive maintenance. The transformer isn't displaying any abnormality. The heat distribution in the windings appear normal, and the operating temperature is within acceptable limits. This cable end terminal is visibly hotter than its neighbors. The thermographer suggested that it should be repaired in the near future, and that the electrical load should be monitored as a precaution. Fuses in this fuse box displayed a serious thermal abnormality. The fuse was immediately replaced. Some line traps in this switchyard warrant inspection. Thermography shows temperatures over 60 degrees Celsius. They should be inspected for physical damage and looseness in the very near future. Heat distribution across the windings of this motor shows some abnormality. Maximum temperature on both sides exceeds 90 degrees Celsius. Close observation was recommended. Mechanical problems give rise to forces that may result in heat generation. The obvious example of this is friction. Thermography is thus a useful tool, enabling inspection of machine components such as couplings, pulleys and belts without needing to stop the machine. Thermogram indicates a distinct thermal abnormality that suggests a severe misalignment in this belt drive. Thermal abnormality is evident on the non-drive end bearing. Additional checks including lubrication and vibration analysis were suggested as means of obtaining a more specific diagnosis. This thermogram indicates that the temperature on the right-hand side compressor head is 10 degrees Celsius higher than on the left-hand side. Further temperature variation would be indicative of improper valve operation. It was recommended that the machine be inspected again after a month to check for deterioration. Weakened insulation on the lower pipe of this heat exchanger is clearly visible. The thermogram identifies thermal variation above 60 degrees Celsius among the rolls. This will also affect product quality. An additional survey after rectification would provide evidence that the problem had been solved. This thermogram identifies a thermal abnormality in trap number 4 and in the last two traps from the left. This thermogram for a turbine suggests that the insulation on the inlet pipe has been damaged. A thermographic study of this furnace clearly indicates an abnormality in the surface heat distribution, possibly resulting from damage to the refractory lining. He makes the breakdown of the insulation in this cement kiln clearly visible. Surface temperatures above 500 degrees Celsius were evident. Thermography detected a weak joint on the side of this steam main stop valve. Thermogram indicates a problem with the exhaust duct from a gas turbine. Here's a quick summary of the lesson. You've now seen examples of what a thermogram can look like.